In previous videos, so far we've seen exponential functions with bases like 2 and 1/2. In many applications, the most convenient choice for a base is the irrational number e, which is approximately equal to 2.718, known as Euler's number. There are a few different ways that this number can be defined. Let's take a look at some of them. So Euler's number e can be defined in some of the following ways. E is equal to the infinite sum of 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3, and we can keep continuing that pattern. So it turns out that not only can I add up all of these fractions together, even though there's infinitely many of them, not only am I going to get a finite number as their total sum, but that number also just happens to be e. How interesting. Another way that we can get e is if you consider the n behavior of the function f of n is equal to 1 plus 1 over n to the nth power. As n goes to infinity, this function, its output values approach the number e. Finally, the third way we can define it is, suppose that you have the graph of the function f of x equals 1 over x. Let's say that you shade the area underneath the curve starting at x equals 1 to some number x equals question mark. If you require that area underneath the function curve, and here you can see it's shaded in blue. So if you require that shaded blue region to have an area of 1 square unit, then the x value must be e, Euler's number. So those are just a few ways that we can define this interesting irrational number e. Example 1 says use a calculator to fill in the table below for the function f of x equals e to the x and g of x equals 2 times e to the power of negative 0.24x. Round your answer to 3 decimal places. So basically this is just to help us gain practice for us to plug in values using specifically the number e in our calculator. So I think it'll be easier if we start off with x equals 0. So if we evaluate f of 0, that's going to be e to the 0 power, which that's going to equal 1. So I'm going to go ahead and put a 1 here. For g of 0, we would have 2 times e to the negative 0.24 to the 0 power, and my exponent, that's all just going to become 0. And if we're following order of operations, e to the 0 is 1, so we're going to have 2 times 1, which finally will equal 2. And that shouldn't have been surprising, since here that is basically our a value or our starting value. So if I raise e to the first power, so now if we're plugging in 1 for our exponent, that's just going to give us the number e, and it tells us to round to 3 decimal places, so that's going to be 2.718. For the rest of these, we're probably going to need a calculator, so go ahead and pause the video and enter these into your calculator, and just make sure that you're able to get the same correct answers that I'm about to put on the screen in just 1 second. All right, so here are the values. Now, one thing that you might notice in f of x, our y values are increasing as we increase the x values, and our g of x values, those are decreasing as x is approaching infinity. So that's just something interesting to notice, and the reason that the g values are decreasing is if we write out our g function, g of x is equal to 2 times, and then our common ratio is going to be e to the negative 0.24, and then our exponent is x, and our output values or our g values are decreasing because if you threw this number e to the negative 0.24 into your calculator, that number happens to be between 0 and 1, and so because of that, we have exponential decay. So just as a quick reminder, in general, exponential functions look like y equals a times b to the x power, and if b is greater than 1, then we have exponential growth, and if b is between 0 and 1, then we have exponential decay. Okay, let's move on to example 2. Example 2 says, the zombie apocalypse has begun. Oh no! It starts in a small city with 10,000 people. After t days, the number of people that have become zombies is modeled by the function z of t is equal to 10,000 over 5 plus 1245 e to the negative 0.97t. Part A says how many people are zombies initially, in other words, when t equals 0. So what we want to do for part A is we want to evaluate z of 0. So anywhere I see a t, I'm going to replace that with a 0. And if I multiply negative 0.97 times 0, that's just going to give me 0. And we know that e to the 0 is 1. So then I'm going to now replace this with 1. That's going to become 10,000 over 1245 times 1 is just itself. And if I add that with 5, that should give me 1250. And then that just ends up simplifying to 8. So there are 8 zombies initially. All right, part B says, find the number of zombies after 1 day, 2 days, and 5 days. So part B is just a way for us to get more practice plugging in the natural exponential function into our calculator. So after 1 day, if we're rounding to the nearest whole zombie or whole number, after 1 day there will be 21 zombies, after 2 days there will be 54 zombies, and after 5 days there will be 678 zombies. So just make sure that you're able to plug these into your calculator and get the same number that I am on the screen. Now, it turns out that this function here, z of t, is actually a special kind of function, and this is called a logistic model. And you study these more in depth when oftentimes in biology, because they represent, logistic models often represent population growth. And because when we graph this, there's some starting point, and usually it looks something like this, and there is some kind of horizontal asymptote here. And so we kind of want to find that in part C. It says what happens as time goes on. So, oftentimes we think, oh, everyone's going to become a zombie. That might not necessarily be the case. So let's kind of see what happens as t gets really, really large. All right, so for part C, we're basically saying as t goes to infinity, what is happening to z of t? So I've written out some of the function here, and for the last part, instead of writing it as it stands on the page or the screen right now, I'm going to rewrite e to the negative 0.97t, and because our exponent's negative, this is the same thing as 1 over e to the, and now we can make the exponent positive. So I did that because I think it's going to be a little bit easier to see now what's going to happen as t gets really, really large. So I have this fraction inside this parenthesis, and t is getting very, very large. And notice that the numerator of this fraction is 1, and that's going to stay constant. So e to some really, really large exponent is going to be a super huge number. And if I have 1 divided by a super huge number, that is essentially going off to 0. So what I can say now is that this is going off to 10,000 over 5 plus 1245, and this is essentially becoming 0 as t goes to infinity. And so what's going to happen is this is all going to become 0, so 5 plus 0 is just 5. And so we're going to get 10,000 divided by 5, and that's going to equal 2,000. Now, you might be asking yourself, why is it 2,000? Well, first of all, this number here is called the carrying capacity. And this basically, if we go back to this graph that I drew here, this basically is us looking at our horizontal asymptote in this case, and it's almost like a limit or an upper bound. The reason that this might be happening here is that even though we're modeling a zombie apocalypse, more realistically, we could use this to model something like some kind of disease or outbreak that's contagious and stuff like that. So in certain instances like this, some people have natural immunity to certain types of diseases. And, when we're talking about the zombie apocalypse, maybe certain people have bunkers and they stay there throughout the whole thing. So we don't necessarily want to assume that all 10,000 people are going to get infected with the zombie virus. So that completes this example and part C. So what happens as time goes on? We expect 2,000 people to become zombies. All right, let's move away from talking about zombies and go back to talking about money. In a previous video, we talked about compound interest. So recall that if you have a savings account with an annual interest rate of R compounded n times per year, then after t years, an initial amount of money P will grow to the amount P times 1 plus R over n to the power of n times t. Now, a question is, what do you think would happen if we were getting interest all of the time instead of just a finite number of times per year? Because in this formula right here, we're only able to use this if n is some finite number, but what if we were getting interest all the time instead of just monthly or weekly or daily? So let's go ahead and rewrite this function above f of t as p times 1 plus r over n to the nt power. What I'm going to do is I'm going to rewrite this slightly. So I'm going to write it as p times 1 plus r over n to the power of n over r times rt. Now, I just edited the exponent slightly, but notice that if I were to multiply n over r times r, this r in the numerator and this r in the denominator would cancel out, and it would return to an exponent of n times t. So that's okay for us to do, because again, if we multiply them, that will give us the original exponent. So now I'm going to do something kind of interesting. I'm going to say let m equal n over r. So I'm going to go ahead and make a substitution now inside of my equation. And I'm going to say that this thing is equal to p times 1 plus. Now, notice that I've defined m to be n over r, and here we have r over n, so that is the reciprocal of m. So I'm just going to rewrite this as 1 over m, since they are reciprocals of each other. And then n over r, I can just, in my exponent, substitute that with m, and then we have times r times t inside of our exponent. Now, another thing that I'm going to do is I'm going to place brackets here, and that's okay. If you remember from previously using exponent laws, if I have something like x to the a power all raised to the b power, this is equivalent to x to the a power times b. So it's okay that I'm adding these brackets down here. And it's going to be a little bit clearer why I'm doing that, or it should. So what we're doing now is, because the number of times that we are compounding is going off to infinity, remember, n represents the number of times that we are compounding per year. So if n is going off to infinity, that also implies that m is going off to infinity, because r is a constant. It is not changing. It's just some interest rate. So if n goes to infinity, that implies that m is also going off to infinity. And in this set of parentheses here, this whole expression, as m approaches infinity, this is approaching p times e to the power of rt. And we know that because the thing inside of our brackets, this thing here, we've seen this before in our definition of e. Let me return that definition to you really quickly. So we have this really interesting function from earlier, and we said that this function, it has the property such that if you have the input value go off to infinity, then the output value of this function approaches the number e. And the only difference is we wrote it so that it was 1 plus 1 over m to the mth power, but m is just representing the input variable, and really that could be replaced with anything. So as m goes to infinity, then this thing goes off to e. So that's why we end up with the formula that we did, where we have p times e to the power of rt. So I'm going to go ahead and just box this here. And let's talk about this formula a little bit more. So p times e to the power of rt represents the formula for continuously compounded interest, meaning we're gaining interest all of the time. Continuously compounded interest is calculated by the formula a of t is equal to p times e to the power of rt, where a of t equals the amount of money after t years, p is the principal amount of money, and remember, principal just means the amount of money that we're starting off with, or the amount of money that you're initially putting into your bank account. R represents our annual interest rate, and t represents the number of years that we are looking at. So let's go ahead and use this information now to look at an example. Example 3 says, a total of $1,000 is invested at an annual interest rate of 12%. I do just want to pause here and say having an annual interest rate for a savings account of 12% is extremely high and not realistic. So I just want to put that in as a caveat. Find the balance after 3 years if it is compounded twice per year. So part A, we are only compounding twice per year, so we need to use the function f of t is equal to p times 1 plus r over n to the power of nt. In this particular case, p is our principal, which is $1,000. Our interest rate is 12%, so I'm going to write that as 0.12 in decimal form. The number of times we're compounding per year is 2, because it says twice per year. And then our exponent is going to be 2 times t. Now I can actually clean this up a bit. So f of t is equal to 1,000 times 12% divided by 2 is 6%, or 0.06. If I add that to 1, then that's going to give me 1.06. So here's our generalized formula for how much money we'll have after t years if we're compounding twice per year with our annual interest rate of 12%. So now what I want to do is I want to evaluate f of 3 and plug in 3 for t. Okay, so if we simplify that, our exponent's going to be 6, and I'm just going to take this and round it to the nearest cent. So if you throw this into a calculator, you'll find, given these circumstances, after 3 years, you will have a total of $1,418.52. So that's it for part A. All right, for part B, we want to figure out the same circumstances. We are just now compounding monthly. So we still are starting off with $1,000, and our interest rate is 12%, and the number of times that we're compounding is 12, so that means that our n value is 12. Okay, so now what I want to do is I want to, well, we could simplify this. The inside, we'd have 1,000 times 1.01, and then our exponent would be 12 times t. And then from here, we could once again evaluate f of 3, so that'd be 1,000 times 1.01 to the 12 times 3 power, and if we simplified that, our exponent would be 36. I'm going to throw this into a calculator and find that our total balance comes out to $1,430.77. So that's if we're compounding monthly. All right, so now we finally get to use the PERT formula, because in part C we are compounding continuously. So we can, and I'm just calling it A of t to match this formula here. You can call it f of t, you could call it g of t, you could call it f of x, but here I'm just having it match this formula. And remember, A of t is just the name we're giving to the function. So A of t is equal to p times e to the power of rt. Our principal amount is 1,000 times E, and our interest rate here is 0.12, and then we have T. So if I wanted to evaluate A of 3, then we have 1,000 times E to the 0.12 times 3. And if we were to throw that into a calculator, that would come out to about $1,433.33. And that should be a reasonable answer because you should be gaining more money if you're compounding more per year. So if we're compounding all throughout the year, then we would expect that to be more than what we found in parts B and part A, which it is. Not by a ton, but compound interest over a long period of time adds up and can make a huge difference. So this completes example 3 and us talking about the natural exponential function. Thanks for watching.